The transesterification of biodiesel takes place by the following reaction. A typical molecule of biodiesel has the following structure. Mostly, it is a long chain of carbon atoms with hydrogen atoms attached. It also has an ester functional group attached at one end, just like all esters do. In the transesterification of biodiesel, we are essentially converting vegetable oil into biodiesel. This reaction can be carried out because vegetable oil, like biodiesel, is an ester. This is a typical structure of vegetable oil. In the transesterification process, methanol is added to vegetable oil. The addition of methanol causes the blue section, which is the backbone of the vegetable oil molecule, to break off and eventually become the glycerol. At the same time, the red bonds in the vegetable oil structure are also broken. These red bonds are then placed with bonds to methoxy groups from the methanol added, resulting in the following structure shown in green. Biodiesel and glycerol are thus produced from the transesterification reaction.
This works by providing a different route with lower activation energy for the reaction, and in the diagram, it's obvious that the activation energy with catalyst is much lower than the activation energy without catalyst. And what is important is that catalyst speeds up the reaction but not increase the U, and therefore the equilibrium remains unchanged. And what the catalyst does is that it accelerates both the forward and backward reactions, so that the equilibrium constant is unchanged. Homogeneous catalysts are defined as catalysts that are in the same state as the reactants, and examples would be aqueous catalysts in aqueous reactants such as sulfuric acid in the formation of esters. However, they have problems because due to their homogeneous nature, the catalysts and reactants are hard to separate, resulting in extra work being needed. Heterogeneous catalysts are catalysts that are in the different state as the reactants, and due to this, they are easier to separate from the reactants. And examples of heterogeneous catalysts would be iron particles in the contact process. Most of the time, heterogeneous catalysts are supported, and supports are porous materials with a high surface area so as to increase the effectiveness of the catalyst.
To catalyze this reaction, we need a catalyst that is in solid form to allow easier separation of the products. We use chitin, which is a polymer that can be naturally found in many organic substances. A polymer is a chemical compound or mixture of compounds consisting of repeating structural units. This is the structural formula of chitin. Chitin is a long-chain polymer that can be found in the exoskeletons of crustaceans and insects. Prawn shells contain 35% chitin by mass, thus they are suitable for the extraction of chitin. It is also environmentally friendly. By carbonization, which is the conversion of an organic substance into a carbon or carbon-containing residue, the chitin can be extracted from the shell. After that, modifiers such as potassium fluoride or potassium carbonate were added. This reacts with the hydroxymethyl group and forms CH2OK, which is the active site for catalysis. After this reaction, the chitin becomes more porous due to the loss of CO2, H2O, and acetyl group. This will be effective in catalyzing the reaction.
When cooking oil and methanol, both aqueous, react to give you biodiesel and glycerol, the reaction is reversible. Hence, there is a need to push the equilibrium to the right to ensure high yield of biodiesel. There are three ways in which the equilibrium of the reaction is affected: temperature, concentration, and pressure. To the production of biodiesel, in this case, to ensure a higher percentage of reaction yield, we can increase the concentration of alcohol. Excess alcohol is used to drive the reaction to the right and ensure all is totally converted to its esters. They can be later removed by distillation. For the use of catalyst, we will replace the sodium hydroxide catalyst with a heterogeneous catalyst, as liquid catalyst will be troublesome for separation and will lower the quality of biodiesel. This will help to increase the rate of reaction to form products faster through lowering the EA. The reaction mix is kept just above the boiling point of alcohol, around 70 degrees, to speed up the reaction. So the temperature is kept low, as the esterification process is exothermic. Hence, lowering the temperature will drive the reaction to the right, favoring the products.